The cosmos began in total darkness before the first stars ever flickered to life. In that profound emptiness, black holes may have acted as cosmic gardeners, planting the seeds for the very first galaxies. By the end of this journey, you will see how the universe's most destructive forces could also be its greatest creators. We will uncover how these gravitational monsters nurtured infant galaxies and why their ancient light still holds unanswered questions. What does it mean for our origins if the universe was built from darkness? That hot, dense soup of particles was the universe's first and only state of perfect order. For hundreds of millions of years, it expanded and cooled into a vast, silent sea of hydrogen and helium gas, shrouded in utter darkness. This was the cosmic dark ages, a time before stars, before light, before anything we would recognize as a galaxy. Yet this simple, uniform cosmos was not perfectly smooth. Woven into its fabric were the faintest of wrinkles, tiny spots where the density was just a fraction higher than the surrounding area. These minuscule overdensities were the quantum echoes of the Big Bang itself, the universe's first and most fragile structures. They were the only potential the cosmos had for building something more. But these seeds were so weak, their gravitational pull so pitifully small, that on their own they would have taken an eternity to grow. This pristine blank slate sets the stage for our central mystery. How did the universe leap from this near-perfect uniformity to the brilliant, structured cosmos we see today? Something had to give these fragile seeds a colossal head start. Into this silent struggle stepped a different kind of gravitational monster. Most black holes we know about are the tombstones of dead stars, but the first black holes might have been something else entirely. They could have been born directly from the fire of the Big Bang itself. These are known as primordial black holes, and they are one of the most captivating what-ifs in all of cosmology. Imagine a universe less than a second old, a seething, ultra-dense soup. Within that chaos, tiny pockets of space could have become so intensely packed with matter that their own gravity caused them to pinch off and collapse, not into a star but straight into a black hole. They did not need to wait for stars to live and die. They were there at the very beginning, cosmic elders present from the first moments. Their possible sizes are staggering, ranging from something as light as a small asteroid to objects weighing thousands of times more than our Sun. This means that while the universe was still a dark, simple sea of gas, these primordial black holes were already there, dense knots of pure gravity scattered throughout the emptiness. They were not the end of things, they could have been the start of everything. Their mere presence would have warped the space around them, creating gravitational wells that the surrounding hydrogen and helium gas could not resist. So, before a single star could even think of igniting, these ancient black holes may have already begun gathering the raw materials for construction. How exactly could a single point of darkness coax an entire galaxy into being? The answer lies in a cosmic competition for food. But those primordial black holes were not the only possible seeds for cosmic structure. To find another, we must look toward the light. At the hearts of nearly every large galaxy we see today, including our own Milky Way, there lies a gravitational monster of almost incomprehensible scale. These are supermassive black holes weighing in at millions, even billions of times the mass of our Sun. Their existence poses a profound and urgent puzzle for astronomers. How did these giants grow so enormous when the universe was still so young? We see quasars, the intensely bright beacons powered by these voracious black holes, shining from the cosmic depths when the universe was less than 1 billion years old. For them to have grown that massive that fast, they could not have started from the tiny remnants of dead stars. They needed a colossal head start. The answer may be that they were born big. This is the theory of black hole seeds. Imagine two possible paths to a giant's birth. The first path involves the very first stars. These were not like the stars we see today. They were behemoths, hundreds of times more massive than our sun, burning hot and fast. When such a star reached the end of its brief life, it could have collapsed directly into a black hole weighing perhaps 100 solar masses. That is a substantial seed, but for some, it may not have been enough. An even more dramatic path is direct collapse. In the dense, chaotic environment of the early universe, an entire massive cloud of primordial gas could have collapsed under its own weight, skipping the star formation stage entirely. It would have crumpled directly into a black hole with a starting weight of tens of thousands, maybe even 100,000 solar masses. That is not just a seed, it is a fully formed gravitational fortress from the moment of its birth. With such a massive starting point, these seeds were primed for explosive growth. Their immense gravity would have acted like a powerful cosmic vacuum, pulling in the vast reservoirs of hydrogen and helium gas that surrounded them. As this gas spiraled inward, it would have formed a superheated disk, releasing unimaginable amounts of energy before crossing the event horizon. This process, called accretion, is how black holes eat and grow. A seed born with 100,000 solar masses has a tremendous advantage over a seed of just a few dozen. Its gravitational pull is far stronger from the outset, allowing it to consume matter at a phenomenal, record-breaking rate. This positions the supermassive black hole not as a later addition that moved into a pre-built galactic city, but as a potential architect that was there from the very first day of construction. Its powerful gravity could have drawn in the raw gas that would eventually form the galaxy's first stars, and its intense radiation and outflows may have regulated that very formation. The growing black hole and its nascent galaxy were locked in a complex, intertwined dance, each influencing the other's destiny. This intimate interplay between the darkest objects in the universe and the birth of light is one of the most active and thrilling frontiers in our quest to understand the cosmic dawn. This voracious feeding does more than just make the black hole grow. It unleashes a storm of cosmic consequences. As vast amounts of gas spiral inward, friction heats it to millions of degrees, causing it to glow with intense radiation across the entire spectrum. From the poles of this spinning monster, magnetic fields can funnel material into jets of charged particles that scream across space at nearly the speed of light. This energetic outburst is the black hole's way of communicating with its growing galaxy, a language of force and fire. The effect of this conversation is a cosmic paradox. On one hand, the intense radiation and howling jets can blast into surrounding clouds of gas, heating them up and blowing them apart. This pushes the raw material for new stars far away, effectively slamming the brakes on star formation in the immediate vicinity. Astronomers call this negative feedback, a way for the black hole to limit its own fuel supply and prevent the galaxy from growing too fast. It acts like a cosmic thermostat, keeping the galactic core from overheating with too many new stars. Yet, in a stunning twist, the very same forces can also create. When those powerful jets and radiation shocks plow into more distant, colder gas clouds, they do not always destroy them. Instead, they can compress them, squeezing the gas until gravity takes over and collapses the cloud into a dazzling new cluster of stars. This is positive feedback, where the black hole's destructive power becomes a creative force, triggering starbursts across its galactic domain. These outflows do something else, something vital for our own existence. They act as cosmic delivery trucks, carrying newly forged heavy elements out into the void. Inside the superheated maelstrom around a feeding black hole, atoms are smashed together, creating elements like carbon, oxygen, and iron. The black hole's winds then scatter these enriched materials far and wide, seeding the intergalactic medium with the building blocks for rocky planets and ultimately for life. This intricate feedback loop is the missing piece in our puzzle. It shows us that a growing black hole was not a passive passenger in a developing galaxy. It was an active, dynamic governor. By turning star formation up or down, and by spreading essential elements, these gravitational giants could have orchestrated the growth of the first galaxies with a surprising degree of control. Their violent energy might be the very reason why galaxies in the young universe assembled themselves with such breathtaking speed and efficiency. But how do we test such a grand idea? The answer lies in catching these ancient architects in the act. The sheer weight of a black hole fundamentally alters the landscape of space itself. It carves out a deep gravitational well, a pit in the fabric of the cosmos so profound that everything nearby is drawn toward it. In the sparse, quiet expanse of the early universe, this well acted as a cosmic anchor. Picture a single, heavy stone dropped into the center of a still, misty pond. The stone does not just sink, it pulls the very surface of the water downward, creating a deep depression. All the tiny water droplets and particles of mist slowly, inevitably, drift down the slope toward that lowest point. A black hole's gravity did the same thing to the primordial gas and the invisible dark matter that filled the young cosmos. From vast distances, this material began to slide down the invisible slopes of space-time, gathering in a growing halo around the gravitational anchor. This accumulating mass was the raw fuel, the reservoir from which the very first stars would eventually spark to life. But the black hole did more than just gather material. It also provided a crucial element of stability. In those early times, a massive cloud of gas on its own would tend to fragment and collapse into many small, scattered stars. The powerful central gravity of the black hole, however, acted as an organizing force. It held the proto-galactic cloud together, preventing it from flying apart or collapsing too chaotically. This allowed the cloud to grow much larger and more coherent, like a city forming around a central citadel rather than 100 scattered villages. This anchoring process solves a critical puzzle of the cosmic dawn. It explains how those faint, fragile wrinkles in the universe's fabric could have gathered enough material, quickly enough, to become the brilliant islands of light we know as galaxies. The black hole was not merely a later occupant that moved into a ready-made galactic home. The evidence suggests it was the cornerstone, the foundational piece upon which the entire structure was built. Its immense gravity laid down the blueprint, setting the stage for everything that would follow. And from that organized chaos, the first light was about to break. The James Webb Space Telescope is now acting as our ultimate time machine, peering back to an era when the universe was in its infancy. Its unprecedented vision has delivered a stunning revelation. Many of the earliest galaxies it has observed are not the small, fragile collections of stars we expected. They are already massive, complex, and remarkably mature, appearing far sooner than our best models predicted. This is like finding a fully grown forest in a world we thought was only just sprouting its first seeds. Even more telling, the brilliant, unmistakable signatures of quasars have been spotted at the hearts of some of these primordial galaxies. These are the beacons of supermassive black holes in the act of feeding, shining with the light of 1 trillion stars. To find such a powerful, fully developed engine at the core of a galaxy, when the universe was less than 1 billion years old, is a profound puzzle. It suggests these black holes did not arrive late to a pre-built galactic home. They were present at the very foundation. The light captured by Webb is not just a picture, it is a data-rich message from the cosmic dawn. By dissecting its properties, astronomers can estimate the masses of both the galaxies and their central black holes. The relationship they are finding is telling a story of co-evolution, an intertwined growth spurt where the galaxy and its dark heart seem to have built themselves up together. This intimate connection, observed at such an early epoch, is one of the strongest pieces of evidence we have that black holes were not mere byproducts of galaxy formation, but may have been the very architects that accelerated it. The data is forcing us to redraw our cosmic timelines and seriously consider that the first great structures were born from a partnership between light and unimaginable darkness. These digital universes are our most powerful tools for rewinding time. Inside the world's most advanced supercomputers, astrophysicists are building virtual cosmos from the ground up, starting with the near-uniform gas of the Big Bang and letting the laws of physics play out. They can plant different kinds of black hole seeds into this primordial soup and then watch over billions of simulated years what kind of galaxies sprout from them. The results are striking. In simulations that include these early gravitational anchors, the emerging galaxies often look remarkably like the ones we actually see with telescopes like James Webb. The black holes do not just sit there, they actively participate. Their ferocious energy output acts as a cosmic pressure release valve. Without this feedback, the virtual galaxies have a tendency to go wild, converting nearly all of their gas into stars in a short, brilliant burst. They become too massive, too blue, and too bright, ending up as cosmic behemoths that do not match the more diverse reality we observe. But when the model includes the energy from an accreting black hole, something beautiful happens. The intense radiation and powerful jets push back on the inflowing gas, slowing down the star-making process. It is a balancing act between creation and destruction. The black hole's fury prevents the galaxy from burning through its fuel too quickly, allowing it to grow in a more regulated and sustained manner. This explains how some early galaxies could achieve both great mass and a mature structure without collapsing under their own weight. These simulations allow scientists to run countless experiments, testing what happens if the first black hole seeds were small, from collapsed stars, or if they were born as supermassive giants from direct collapse. The virtual cosmos becomes a testing ground for our deepest questions, narrowing down the possibilities of how our own universe might have unfolded. The harmony between what we see in the sky and what we see in the code is the strongest hint that we are on the right track, uncovering the true story of how darkness built the islands of light we call home. The timing problem is a cosmic head-scratcher of the highest order. We see quasars powered by black holes weighing billions of suns, shining from an era when the universe was just a toddler. For one of these monsters to reach such a staggering size in under 1 billion years, its feeding frenzy would have to be nothing short of perfect. It would need to devour matter at the absolute maximum speed physics allows, a rate called the Eddington limit, and maintain that incredible pace for its entire life without a single pause. Think of trying to fill a swimming pool with a fire hose running at full blast, day and night for centuries. That is the kind of relentless consumption required, a scenario that seems almost too ideal to be true. So astronomers have proposed other, more dramatic pathways. Perhaps these giants did not start small at all. They could have been born as supermassive infants from the direct collapse of enormous gas clouds, giving them 100,000 solar mass head start. With that kind of initial weight, their gravitational pull was immense from day one, allowing them to pull in gas far more effectively and rapidly close the gap to 1 billion solar masses. Another possibility lies in cosmic collisions. The early universe was a much more crowded and chaotic place. Black holes, once formed, could have drifted together and merged, their gravitational dances culminating in violent unions that created a single, more massive object. This is like several smaller streams converging to form a mighty river, a growth strategy that does not rely solely on steady accretion. Yet even mergers need a rich environment full of black holes to combine. The true solution likely involves all these mechanisms working in concert. A massive seed black hole, born from direct collapse, settles into the heart of a vast reservoir of cold, dense gas. It feeds at a super-efficient rate, perhaps even exceeding the Eddington limit in brief, violent bursts. All the while, it merges with other black holes that have been drawn into its gravitational domain. This paints a picture of the early cosmos not as a serene and gentle place, but as a dynamic, violent, and incredibly efficient factory for building giants. Unlocking the secret to this rapid growth is not just about understanding black holes. It is about validating the entire idea that they could have been the architects of the first galaxies. If they could not grow fast enough, then they could not have exerted their influence in time to shape the cosmic dawn we observe. The puzzle of their speed is the linchpin holding this entire grand story together. But this entire cosmic construction project relied on an invisible framework. The gravity of the black hole and the gas alone was not enough to build a galaxy. They needed the unseen hand of dark matter. This mysterious substance, which does not emit or absorb light, makes up the vast majority of the universe's mass. Its presence is felt only through its immense gravitational pull. In the young cosmos, dark matter was the first to get to work. It collapsed into enormous, spherical structures known as halos, vast and invisible clouds of gravitational potential that served as the foundational blueprints for everything to come. Think of a dark matter halo as the steel frame of a colossal, invisible skyscraper. Long before any walls or windows are added, that frame defines the building's shape, size, and strength. It is the underlying structure that determines what can be built upon it. The gravity of this dark matter frame then began to pull in the ordinary atomic matter, the baryonic gas of hydrogen and helium that had been drifting in the darkness. This gas was the building material that would eventually form stars and planets. Now, place a central black hole seed right at the heart of this growing system, nestled deep within the dark matter halo. This is where the story becomes incredibly intricate. The black hole is not just a passive object sitting at the center. It becomes an active player in a three-way gravitational dance. Its powerful pull can alter the very way the gas behaves as it flows into the halo. Normally, the gas would swirl and collide, fragmenting into many smaller clouds to form stars scattered throughout the proto-galaxy. But the black hole's gravity can act like a cosmic traffic controller, funneling streams of gas more efficiently toward the very center. This direct delivery service does two things simultaneously. It feeds the black hole, allowing it to grow rapidly and potentially unleash the feedback that regulates star formation. At the same time, by siphoning gas toward the center, it might actually prevent the outer regions of the halo from forming stars too quickly, shaping the entire galaxy's structure from the inside out. This complex partnership between the invisible dark matter scaffolding, the flowing river of ordinary gas, and the central black hole engine is one of the most challenging puzzles in modern cosmology. How exactly did these three components work together to transform a faint ripple in the cosmos into a brilliant, stable galaxy? Cracking this code is essential because it means the birth of light was a symphony conducted by both the seen and the unseen, a collaboration between the darkness we can detect and the darkness we can only infer. The first stars were pure and simple, giants made only of hydrogen and helium. When they exploded, they scattered the very first heavy elements into the void, a foundation for all future chemistry. Yet they were not the universe's only alchemists. Lurking in the galactic core, another, more violent forge was at work. As a supermassive black hole feeds, the incredible temperatures and pressures in its accretion disk can smash atoms together, cooking hydrogen and helium into a richer blend of elements like carbon, oxygen, and iron. But these newly forged ingredients would be useless if they remained locked in the black hole's deadly embrace. They need a delivery system, and the black hole provides one with tremendous force. The intense radiation and magnetic fields power vast outflows, cosmic hurricanes that scream outward from the galactic center. These winds and jets act like a colossal distribution network, gathering up the enriched material and hurling it far beyond the galaxy's core, out into the vast reservoirs of pristine gas between galaxies. This process, known as mechanical feedback, does more than just clean out the central engine. It pollutes the entire neighborhood. It seeds the cold, primordial gas clouds with the essential elements for planet building. Imagine a farmer scattering nutrient-rich compost over a vast, barren field. That field is the intergalactic medium, and the compost is the elemental building blocks for rocks, oceans, and air. Without this cosmic recycling program, the universe might have remained a place of simple hydrogen and helium stars, with no solid planets, no water, and no chemistry complex enough for life to ever emerge. The black hole's destructive fury becomes a creative act, a vital step in transforming a primitive cosmos into one brimming with potential. This means the very iron in your blood and the calcium in your bones may have been forged in a galactic heart of darkness, then blasted across the cosmos on a wind of pure energy, waiting billions of years to become part of you. These invisible lines of force are the universe's silent conductors. Magnetic fields thread through the cosmos, and around an early black hole, they became instruments of immense power. Picture the furious whirlpool of an accretion disk, a maelstrom of superheated gas spiraling toward oblivion. Within this chaos, the gas is ionized, its atoms stripped of electrons, creating a perfect environment for magnetic fields to grow. As the disk spins, these fields are stretched, twisted, and amplified, woven into ropes of immense energy. They do not just sit there, they actively fight back against the crushing pull of gravity. This magnetic struggle finds its most spectacular release in the jets. Like cosmic lightning rods, the black hole's poles channel this pent-up energy, funneling material into two narrow, incredibly focused beams that scream across space. These are not diffuse explosions, they are precision tools. A jet can punch through a galaxy, delivering a targeted burst of energy and momentum into the gas clouds tens of thousands of light-years away. This is feedback on a galactic scale, but with a surgeon's precision. The magnetic fields carried within these jets do something else, something more subtle than mere pushing. As they plow into the primordial hydrogen, they stir it. They create turbulence, a chaotic churning that ripples through the gas. Why does this matter? Because for a cloud of gas to collapse and form a star, it must be able to cool down. Turbulence makes this process more complex, sometimes preventing a cloud from fragmenting into many small stars, and instead encouraging the formation of fewer, more massive stars. This means the magnetic fields emanating from the black hole could have directly influenced the very recipe for star birth, determining the size and population of the first stellar generations. Unraveling this magneto-hydrodynamic connection, this intricate dance between magnetic forces and flowing matter, is like discovering the fine print in the contract between a black hole and its galaxy. It reveals that the feedback was not just a blunt force of heat and wind, but a sophisticated regulatory mechanism, one that could sculpt a galaxy with an artist's touch. Yet the story of cosmic dawn is far from settled. While the idea of black holes as galactic architects is a powerful narrative, it is not the only one scientists are exploring. Competing theories present a universe where galaxies could build themselves from the ground up, no black hole required. In these models, the invisible scaffolding of dark matter takes the lead role. Vast halos of this mysterious substance form first, their immense gravity slowly pulling in the primordial hydrogen and helium gas. As this gas settles into the halo, it begins to radiate heat, cool down, and condense. This cooling is the critical step. It allows the gas to fragment into dense clouds, which then collapse under their own weight to ignite the very first stars. In this version of events, galaxies assemble themselves naturally through these processes of gravitational collapse and cooling. A supermassive black hole at the center is not the cause of the galaxy's formation, but a possible consequence. It forms later from the incredibly dense pool of gas that naturally accumulates at the galaxy's chaotic core, or from the merger of many smaller black holes born from the first generation of massive stars. The primary challenge for these dark matter-driven models is timing. Can they explain the astonishingly rapid growth of billion solar mass black holes we observe in the early universe? Can they account for the intimate, co-evolutionary relationship between a galaxy's mass and the mass of its central black hole, a connection that seems to exist from the very beginning? To address this, some theorists explore more exotic pathways within these halos. One compelling idea involves dense star clusters. In the tumultuous core of a young galaxy, thousands of stars could be packed into a relatively small volume of space. Through a complex gravitational dance, these stars could collide and merge, eventually forming a single, monstrously heavy star that promptly collapses into a sizable black hole seed. This seed could then grow through accretion, bypassing the need for a single, hypothetical supermassive star or a direct collapse of pristine gas. Examining these alternative pathways is not about choosing a single winner, but about appreciating the full spectrum of cosmic possibility. The true history of galaxy formation is likely not a simple either-or. Our universe is a pragmatic and diverse builder. It is entirely possible that multiple formation channels operated simultaneously. Some of the first galaxies may have been indeed forged around a massive black hole seed, their growth accelerated by its powerful feedback. Others may have assembled more gradually through dark matter and gas dynamics, with their central black holes emerging as late-blooming tenants. This hybrid model, a cosmic tapestry woven from multiple threads, may be the key to understanding the rich variety of galaxies we see in the night sky. The search for our ultimate origins continues, not by seeking one single truth, but by mapping the many roads the universe could take from darkness to light. The hunt for these ancient seeds is a scientific frontier in its own right. If primordial black holes truly helped build the first galaxies, a few of them should still be drifting through the cosmos, silent ghosts from the beginning of time. Finding one, however, is like searching for a single, dark needle in an impossibly large haystack. Their predicted small size means they emit virtually no light of their own, and they are far too faint to see directly with any telescope. So astronomers have turned to clever, indirect ways to sense their presence. One method relies on a prediction from Einstein's theory of relativity, a phenomenon called gravitational lensing. Imagine a primordial black hole drifting silently through space on a path that takes it directly between us and a distant background star. As it passes in front, its intense gravity acts like a tiny, invisible lens, warping the fabric of spacetime and briefly bending the starlight. For a fleeting moment, that faraway star appears to brighten, as if a cosmic magnifying glass has been held up to it. Telescopes across the globe are constantly monitoring millions of stars, watching for these sudden, unexplained flashes that could betray the passage of a hidden, ancient object. Another promising technique listens for the ripples they might create in spacetime itself. When two primordial black holes spiral toward each other and merge, they should generate a unique shiver in the cosmic fabric, a high-pitched chirp of gravitational waves that observatories like LIGO and Virgo could potentially hear. The discovery of even one of these relics would be a landmark achievement. It would confirm the existence of a population of black holes that were never stars, objects born from the raw chaos of the Big Bang itself. Such a find would transform them from a captivating what-if into a tangible reality, providing powerful, direct evidence that they were indeed present in the early universe, ready and waiting to act as the seeds for everything that followed. This extraordinary search is the ultimate test, a quest to touch a piece of the cosmic dawn and finally understand the true architects of our galactic home. This dynamic regulation solves a long-standing galactic mystery. Why do some galaxies blaze with the furious birth of new stars, while others drift quietly as aging stellar communities? The answer may lie in the rhythm set by their central black hole. When a black hole feasts, its intense radiation floods the surrounding space. This energy doesn't just travel outward, it physically heats the vast clouds of cold molecular gas that serve as the raw material for new stars. Think of this gas as a kind of cosmic flour. To form stars, this flour must be cold and dense enough to clump together under its own weight. But when the black hole turns up the heat, it's like placing that flour under a broiler. The individual particles become too energetic and agitated to coalesce. They bounce away from each other, and the entire star-making process grinds to a halt. The galaxy enters a quiet, quiescent phase, its stellar population aging without the spark of new birth. Yet this same engine of suppression can also become a tool of creation. The colossal jets screaming from the black hole's poles act like cosmic plows. When they slam into distant, untouched reservoirs of cold gas, they don't always vaporize it. Instead, they can send powerful shock waves rippling through the cloud. These waves compress the gas, squeezing it so tightly that local pockets of density suddenly cross a critical threshold. Gravity seizes control, and a spectacular burst of star formation ignites. This is the cosmic cycle at its most elegant. A period of furious black hole activity first stifles star birth in the inner galaxy, only to later trigger a starburst on its outer edges. The galaxy doesn't evolve in a smooth, steady line, but in a series of fits and starts, bursts and pauses, all conducted by the gravitational maestro at its core. This explains the breathtaking variety we see across the cosmos, from brilliant blue galaxies teeming with infant suns to serene red galaxies where star formation is all but a memory. The black hole's influence imprints a unique life story upon its galactic host, a story written in the rhythm of stellar fire. This deep connection between black holes and galaxies is not a relic of the ancient past. It is written into the very fabric of the cosmos we see today. Look at any large modern galaxy, and you will find a profound clue. Astronomers have discovered a remarkably tight relationship between the mass of a galaxy's central bulge, the dense swarm of stars at its heart, and the mass of its supermassive black hole. The more massive the bulge, the more massive the black hole. This is not a mere coincidence. It is the signature of a long and intimate partnership, a cosmic dance that has been ongoing for billions of years. This is the principle of co-evolution, where the growth of the galaxy and its dark heart are fundamentally linked. The feedback processes that were so crucial in the chaotic early universe, the violent outflows and intense radiation, are the very mechanisms that carved out this relationship. Think of it as a lifelong conversation between the black hole and its host. When the galaxy feeds the black hole too much, the black hole responds by switching on its powerful winds, pushing back against the incoming gas and effectively turning down the fuel supply. This self-regulation prevents the galaxy from growing uncontrollably and ensures that the black hole does not become disproportionately large. It is a balancing act that has been fine-tuned over eons, leaving this precise correlation as its lasting record. Even in our own seemingly peaceful Milky Way, the supermassive black hole known as Sagittarius, a star, occasionally stirs from its slumber. It flares up, consuming small clouds of gas and emitting bursts of X-rays, a quiet reminder of the dormant power residing at our galactic center. These flickers are echoes of a much more violent youth, a time when our own galaxy was being forged in the crucible of feedback. To truly understand why this relationship exists in the present, we must trace its origins back to the very first moments, to the planting of those initial seeds in the primordial dark. The story of how darkness built the first islands of light is not over. It is still being written in the silent, gravitational bond between every giant galaxy and the ancient monster at its core. The early cosmos was a far more crowded and chaotic place than it is today. In that dense environment, the first small galaxies did not evolve in peaceful isolation. They were constantly drawn together, their gravitational fields intertwining in a violent cosmic dance. When two of these infant galaxies collided, it was not a simple crash of stars. Their stellar populations were so sparse that stars would almost never physically hit one another. Instead, their vast clouds of dark matter and gas would slam together, and this is where the real transformation began. The chaotic forces of the merger would send shockwaves rippling through the galactic gas, disrupting its orderly rotation and funneling enormous rivers of fresh fuel directly toward the center. For a hungry black hole seed waiting in the core, this was a windfall of cosmic proportions. A sudden, massive delivery of gas would trigger a ferocious feeding frenzy, causing the black hole to flare into a brilliant quasar and unleashing a storm of feedback that could reshape the entire newborn galaxy. This galactic cannibalism also solved the problem of how to build truly massive black holes. When two galaxies merge, their central black holes are carried along for the ride. Dragged by the pull of the combined dark matter halo, they begin to sink toward the very center of the new, larger galaxy. As they spiral inward, they first form a binary pair, a tight gravitational dance of two monsters orbiting one another. This dance does not last forever. Through a complex process involving gravitational interactions with nearby stars and the eventual emission of gravitational waves, the two black holes draw closer and closer until they finally coalesce into a single, more massive entity. This merger is a cataclysm of almost unimaginable power, shaking the very fabric of space-time and releasing more energy in a few moments than all the stars in the galaxy combined. This violent union provides a rapid growth mechanism that does not rely solely on steady accretion, allowing black holes to pack on mass in tremendous leaps. This entire process, known as hierarchical assembly, was the universe's primary method of construction. Small building blocks merged to form larger structures, which then collided to form the great galaxies we see today. Each major merger delivered another massive infusion of gas to the center, powering a new episode of black hole growth and energetic feedback. This cycle of collision, feeding, and regulation imprinted itself on the emerging galaxy. The furious bursts of star formation triggered by the merger, followed by the black hole's forceful winds that later suppressed it, carved out the galaxy's final structure. It dictated the size of its central bulge and the distribution of its stars. The remarkably tight relationship we see today between a galaxy's bulge and its black hole mass is not a quiet correlation. It is the fossil record of this ancient, violent history. It is the enduring signature of a universe built through a relentless series of collisions, where chaos and destruction were the essential tools for creating lasting order. For all the elegance of this cosmic story, it rests on foundations we have not yet fully secured. We are still searching for that first, crucial piece of evidence, the direct observation of a primordial black hole drifting through our galactic neighborhood. Its discovery would be a monumental confirmation, but for now, these ancient seeds remain tantalizingly theoretical. The physics governing the early universe also pushes our knowledge to its absolute limits. We struggle to model the precise behavior of superheated gas as it spiraled into those first voracious black holes. How exactly did it swirl, and how efficiently did it cross the event horizon? The answers dictate the speed of growth, and our current models are filled with educated guesses about the complex turbulence and magnetic fields that must have shaped this flow. Even the starting point is shrouded in mystery. Were the first seeds the husks of massive Pop-3 stars, or were they born as supermassive infants from direct collapse? The initial mass function, the cosmic recipe for how many black holes of each size were created, remains one of the field's great unsolved puzzles. Our most powerful tools, the supercomputer simulations, are themselves limited. They can only simulate a tiny fraction of a galaxy with the required resolution, forcing scientists to make approximations for the small-scale physics of star formation and the intricate tangling of magnetic fields. These are not minor details, they are the very forces that sculpted the cosmos. Overcoming these challenges demands a new generation of observatories and technologies. We need telescopes capable of detecting even fainter, more distant galaxies from the cosmic dawn, pushing James Webb to its limits and beyond. We require instruments sensitive enough to hear the faintest gravitational wave chirps from the mergers of the very first black hole seeds, a signal that would tell us their initial sizes and numbers. And we must develop theoretical models of breathtaking complexity, ones that can seamlessly weave together the physics of dark matter, gas, stars, and black hole feedback into a single, coherent digital universe. The path forward is not a straight line to a single answer, but a sprawling frontier of discovery. Each new observation, each more refined simulation, has the potential to solidify our current understanding or to completely revolutionize it, forcing us to rewrite the story of how our universe first sparked to light. The reach of these cosmic architects extends far beyond their own galactic walls. Their furious activity carves its signature into the very large-scale structure of the universe. Picture the most powerful quasars blazing at the hearts of the earliest galaxies. Their radiation and galactic winds do not simply fade away. They flood out into the vast, empty spaces between galaxies, a region known as the intergalactic medium. This primordial gas is the potential fuel for future generations of dwarf galaxies, but the quasar's energy acts like a colossal space heater, warming this gas and preventing it from ever cooling down enough to collapse into new, smaller galactic halos. It effectively raises the minimum size required for a galaxy to form. The consequence is a cosmic suppression of dwarf galaxies, subtly altering the entire demographic makeup of the universe. We might see fewer of these small, faint galaxies than we otherwise would, a lasting echo of that ancient fury. The initial placement of the first black hole seeds themselves could have shaped the cosmos in another profound way. If these seeds were numerous and clustered in specific patterns, their collective gravity would have acted like an invisible template. The ordinary matter, the gas that would become galaxies, would have been drawn to these points of heightened gravity. This means the distribution of the very first black holes could have directly influenced where galaxies preferentially formed, imprinting a specific pattern on the grand cosmic web we observe today, the vast filamentary network of galaxies stretching across billions of light years. Cosmologists are now like detectives examining a cosmic crime scene, looking for these subtle statistical signatures. By mapping the precise clustering of millions of galaxies across space and time, they can search for tiny deviations from the predictions of models that lack this early black hole influence. It is an attempt to read the fossil record of energy injected into the infant cosmos. This incredible connection ties the violent, small-scale physics around a single black hole's accretion disk to the grandest architectural blueprints of the universe. A local event, a feeding frenzy in one tiny corner of space, can ripple outward to shape the entire distribution of light across the heavens. A silent symphony of gravitational waves ripples across the cosmos, carrying the echoes of ancient collisions. To listen to this cosmic hum, we must leave the vibrations of Earth behind. The Laser Interferometer Space Antenna, known as LISA, is a revolutionary mission designed to do just that. It will consist of 3 spacecraft flying in a perfect triangular formation, millions of kilometers apart, connected by lasers. This vast instrument will detect the low-frequency gravitational waves produced by the mergers of those first supermassive black hole seeds. While ground-based observatories hear the high-pitched chirps of stellar mass black holes, LISA will listen for the deep, resonant bass notes of giants coming together in the early universe. A single detection would be more than just data. It would be a direct recording of a foundational moment in cosmic history. It would tell us the masses of those first seeds, revealing whether they were born from collapsed stars or as colossal infants from direct collapse. This is not just listening to the universe, it is auditing its very first construction projects. On the ground, a different kind of revolution is taking shape. The mirrors of the next generation of telescopes are so vast they redefine our reach. The 30-meter telescope and the extremely large telescope will gather more light than all but a handful of the most powerful observatories in history. With this immense light-gathering power, they will not merely see the earliest galaxies as faint smudges. They will dissect their light into exquisitely detailed spectra like a cosmic barcode. From this, we can read the velocity of the gas swirling within these infant systems, mapping the gravitational influence of the central black hole with precision. We will be able to detect the chemical fingerprints of elements forged in their hearts, tracing the pollution from those first stellar generations and the outflows from the active black hole itself. This is the difference between seeing a distant city at night and being able to read the street signs, to measure the flow of traffic, and to sample the composition of its air. These telescopes will transform these ancient galaxies from abstract concepts into dynamic, physical places we can study and understand. The ultimate goal is to push our vision to the very edge of time, to watch the first stars flicker on and the first black holes awaken. Concepts for future space-based observatories, far more powerful than any we have today, are already on the drawing boards. These missions would operate from the pristine environment of space, free from the blurring effects of Earth's atmosphere, and would be designed to see in the infrared with breathtaking sensitivity. They would peer into an era before even the James Webb Space Telescope can easily see, a time when the first structures were just beginning to coalesce from the dark. They would hunt for the direct light from the population 3 stars, the very first ones, and search for the telltale glow from the accretion disks around the very first black hole seeds. This is the final piece of the puzzle. By witnessing this epoch of first light directly, we can finally move from compelling stories about what might have happened to a grounded history of what actually did. The data flowing from these technological marvels will either confirm the black hole's role as the master architect of the cosmic dawn, or send us back to the drawing board in search of a new, even more incredible story of our origins. This cosmic narrative forces us to reconsider the very definitions of creation and destruction. We often see them as opposites, yet the story of the first galaxies reveals them as partners in a single dynamic process. A black hole, the ultimate symbol of cosmic annihilation, becomes the unlikely architect of a galaxy, the very home for billions of new stars. The universe seems to operate on a principle where the most extreme conditions are necessary to forge the greatest complexity. Think of a forest fire. In its immediate wake, it appears to be an agent of pure devastation. But that same fire clears away the old undergrowth, releases seeds from tough cones, and returns nutrients to the soil, paving the way for a new and more vibrant ecosystem to emerge. The black hole's fury acts in a similar way on a galactic scale. Its violent outflows clear regions of gas, but they also trigger new star birth and spread the elements for planets. This is not a universe of gentle, steady growth. It is a cosmos that builds through cycles of intense, transformative violence. Our own existence is a testament to this profound and unsettling truth. Every element in our bodies heavier than hydrogen was forged in the heart of a star or the maelstrom around a feeding black hole, and then scattered across space by these explosive forces. We are not merely living in the universe, we are a product of its most fundamental and contradictory nature. We are here because gravity can create as fiercely as it destroys, connecting our own story directly to the dark engines that lit up the cosmic dawn. The pieces of the cosmic puzzle are finally clicking into place. From the brilliant, ancient galaxies spotted by the James Webb Telescope to the intricate digital universes born in supercomputers, a single compelling narrative is taking shape. It tells us that black holes were the active foremen on the construction site of the early cosmos, not just tenants who moved in after the work was done. Their profound gravity gathered the raw gas, their fierce radiation heated it, and their powerful jets compressed it, triggering the very first bursts of star formation. This dynamic partnership, this constant conversation between the galaxy and its dark heart, is what carved the relationship we see etched across the modern universe. Every time we observe that a galaxy's central bulge is precisely proportioned to its supermassive black hole, we are seeing the fossil record of this ancient, intertwined growth. The story is not yet complete, of course. Gaps in our understanding remain, like missing chapters in an epic novel, yet the overarching theme is unmistakable. The universe did not build its greatest structures gently. It forged them in a crucible of gravitational fury, where the most destructive forces became the most essential creators. The debate over these cosmic architects is far from settled. Across the world, in university halls and virtual conferences, astrophysicists are locked in a vigorous and essential discussion. Those who champion the idea of black holes as primordial seeds argue that it elegantly solves two major puzzles at once. It explains how supermassive black holes grew so incredibly fast in the young universe, and it accounts for the surprising maturity and structure of the earliest galaxies we observe. For them, this is the most coherent story that fits the emerging data. Yet skeptics offer a crucial counterpoint. They remind us that no one has ever directly detected a primordial black hole. Their existence, while compelling, remains entirely theoretical. Furthermore, the physics involved is staggeringly complex. Modeling how gas actually flows into a black hole, how magnetic fields twist and amplify, and how energy is deposited back into the galaxy involves countless approximations. A slight change in one of these assumptions can dramatically alter the outcome of a simulation. turning a brilliant galaxy into a faint smudge or an unrealistic monster. This is not a conflict with clear sides, but a sprawling, collaborative investigation. Scientific papers constantly compare different seed formation mechanisms, testing whether black holes born from collapsed stars are sufficient, or if the more exotic direct collapse model is truly required. They debate the efficiency of feedback, questioning whether black hole winds are powerful enough to regulate an entire galaxy or merely stir the local neighborhood. This vibrant discourse is not a sign of weakness in the theory. It is the very engine of scientific progress. This constant, rigorous questioning pushes astronomers to design more sensitive telescopes, forces theorists to build more sophisticated digital universes, and ensures that every piece of evidence is scrutinized from every possible angle. The final answer will not arrive as a single eureka moment. It will emerge gradually as one line of evidence after another converges, slowly tipping the scales until a new cosmic consensus is born. This grand cosmic construction project holds a secret key to our own existence. The furious activity of those first black holes did more than just shape galaxies. It set the stage for life itself. Think of the universe as a vast kitchen, and the elements are its ingredients. The very first stars could only cook up the simplest elements, hydrogen and helium. But for the complex chemistry of life, you need a richer pantry with carbon, oxygen, nitrogen, and iron. This is where the black hole's feedback becomes a cosmic delivery service. Its powerful winds scooped up these heavier elements forged in stellar furnaces and within its own accretion disk, and scattered them far into intergalactic space. This pollution of the pristine cosmos was essential. It seeded future generations of stars and planets with the building blocks for rocks, oceans, and atmospheres. Without this process, the universe might have remained a place of simple gas giants, with no solid terrestrial worlds like Earth ever forming. The black hole's influence went even deeper, regulating the very pace of cosmic evolution. In a universe without this regulatory force, galaxies might have burned through their gas in a single, brilliant burst of star formation. All the stars would be massive, short-lived giants, exploding as supernova within a few million years. There would be no time for stable, long-lived solar systems to coalesce, no steady, nurturing suns around which life could patiently arise. The black hole, through its violent outbursts, acted as a cosmic pressure valve. By heating gas and slowing star formation, it ensured that galactic fuel was used more sparingly, stretching the process out over billions of years. This created the stable, long-term environments where planetary systems could slowly assemble and life had the time to emerge and evolve. So when we look up at the night sky, we are not just seeing the aftermath of an ancient construction project. We are witnessing the carefully set conditions that made our own world, and perhaps countless others, possible. The dark hearts of the first galaxies may have written the recipe for life long before the first star in our own sun was ever born. Our journey through the cosmos has revealed a universe built not just on light but on profound darkness. The idea that black holes could have seeded the first galaxies represents a true paradigm shift, transforming these gravitational monsters from symbols of pure destruction into generative catalysts for cosmic structure. We have seen how their immense gravity could anchor the first fragile wisps of matter, creating the deep wells that drew in the gas to build galactic homes. We have witnessed how their ferocious energy, through powerful winds and intense radiation, did not merely obliterate but also regulated and triggered the birth of stars. The astonishing speed of their own growth, a challenge that still pushes the limits of our physics, underscores their potential role as central players from the very beginning. Many questions, of course, remain unanswered. The true nature of those first seeds is still a mystery, and the intricate dance between dark matter, gas, and black hole feedback is a puzzle we are only beginning to solve. Yet we are now armed with tools of unprecedented power. The James Webb Space Telescope peers back to the cosmic dawn. Supercomputer simulations recreate entire universes, and a new era of gravitational wave astronomy listens for the echoes of ancient collisions. Together, they are weaving a tapestry of evidence, bringing us closer than ever to understanding our ultimate origins. The overarching story is one of breathtaking interconnection. It suggests that light emerges from the deepest darkness, and that lasting structure is born from the heart of chaos. This means that every single galaxy swirling in the void, every star that dots the night sky, and every world that orbits those stars, including our own, may ultimately carry the subtle imprint of a black hole's ancient seed. Let this incredible story of cosmic genesis inspire you. The next time you look up at the stars, remember the violent and creative forces that forged them, and share this wonder of a universe built from darkness.